The first presenter is Professor Mahesh Tandon. He is the Managing Director of Tandon Consultants Private Limited. Many of the projects designed by Tandon and his firm have received accolades and awards in India and abroad. He was appointed Distinguished Visiting Professor by AICTE-INAE at IITs, that is Kanpur, Roorkee and Gandhinagar during 2005 and 2015. I think people associated with the structures and all, they don't need any introduction of Professor Tandon.
Not at all. I think Professor Tandon is too well known. If you go on repeating it, all it will take too much of time.
Is it there? Which one?
Is there?
Yeah, yeah.
Okay. So there'll be one which is IRC-Hyderabad. Oh. IRC-Hyderabad.
Open करो.
हाँ, open करिए. It doesn't open? How can that be? Bhutan. Number one.
Open.
Yes.
Sir, slider. Do you need slider?
Okay. इसको start कर दीजिए.
एक मिनट. Right, sure. From beginning, no?
Yeah. Good afternoon, friends. It gives me great pleasure to talk about a fascinating bridge in a fascinating country and fascinating surroundings. This is the Punat Sangchu bridge in Bhutan, and you can see the whatever picture that you have, that it is really fascinating. The entire scenario there. This is of course a combined paper. As you know that any major project is a combined effort of many people. So I am just presenting it on the behalf of the 3 people who worked on it. This is the people whom one must give the credit to: the client, contractor, proof consultant, and of course the prime consultant and structural designer. Actually, Punat Sangchu is a 10,000 megawatt hydroelectricity project taken up jointly by the Royal Government of Bhutan and Government of India. Bridge was required to transport heavy equipment of power project such as turbines, transformers, etc. from the national highway to project site, which were on the opposite banks of river Punat Sangchu. Here you can see the main concept was to have cantilever constructions from both the banks. This is the site topography to start with, and after studying many alternatives, this seemed to be the one which seemed most appropriate. This is the sketch showing you that it has got a 114-meter central span and side spans of 29 meters each. So it is a very, very short end spans, and one of the main problems was how to make it stable during construction. And of course, in the service conditions, you have a problem of uplift at the abutment, both the abutments. That is another issue which had to be taken into account. It was a very narrow structure with just 6.5 meter depth width. This can be a big disadvantage when you are designing structures in seismic zone 5 and you have transverse seismic forces. This 6.5 meter may not be adequate. So it was quite a job to get it into within limits of the codes. At that time, IRC 18 and IRC 21. You can see at the ends, you have the main road, and the trucks had to take a sudden right angle bend into this. So on both sides, you have the same problem. So the deck had to be widened when they approach this. Of course, once they are on top of the deck, that then there is no issue. The key challenges were that the requirements was that it had to be designed for a return period, a flood of 1,000 years, and of course the very short end spans which I talked about, and the deck width is extremely small, and that gives you a problem of seismic conditions. The wing walls were extremely tall, and that also created a lot of problems. So these were some of the key challenges that were there in the project. The completed bridge looks something like that, and it looks very beautiful, as you can see. It's really fits into the surroundings, which are hills and a stream. I talked about the wing walls, which were extremely tall. Here you can see the idea of the wing wall is that you should be able to protect from earth, because around this there is all earth on both sides. The bearings, etc., should not come in contact with earth. So these things had to be protected, and these were fairly tall. This is the actual picture of the abutment and the wing walls, which you can see. Section at the central pier is shown here, and you can see that there is about 21 meters of sinking to be done, and this is in some kind of rock which is very difficult to penetrate. But in any case, finally the contractors were Hindustan Construction, and they did manage to get these well foundations down to the bottom. The depth of the superstructure at the central piers is quite large, and they keep on reducing as you keep on coming towards the mid-span. Here it is the minimum depth, and here it is the maximum depth, and you can see that beyond this the depth has been kept constant. The reason is that we want weight to be put on the cartilage, and apart from just keeping a large area of the concrete section, it also has these cartilage, which means that you are putting boulders, etc., in the at the end spans in order to stabilize it. Really speaking, the cantilever construction was done not for the end spans. The end spans were cast in situ, as you can see, on staging, and then we started the cantilever construction before you come to the center, as you can see here. So the center, by the time you reach the depth of the superstructure becomes quite small, and the whole idea is that you should try to reduce the weight in the middle of the span so that you can design the structure. The counterweight, which is something like 8 tons per meter, were put in 2 stages of 8 tons each. Depending on how much is the overturning moment. There is no use putting too much of weight there, because if you do, you may start getting bending moments which are giving you tension at the bottom in the end spans, which is not what you want. At the end spans, you basically should have only tensions at the top. So you have to be careful and judicious about how much of counterweight to put and when. Here you can see that the structure is completed from both ends, and the cast in situ stitch has been done in the middle. The pre-stress cable profiles in the elevation, as you can imagine, most of the cables, because this is all cantilevering out, So most of the cables are at in the top flange and they go right up to the end of the cantilever. After integration of the two cantilevers, it becomes a continuous three-span structure which will create tensions when you put live load in the middle of the span. So you require also bottom cables when you are designing this structure. Apart from that, you also have some cables which are put at the bottom. I think if you read the IRC-112, you will realize that if you have torsions in a box girder, you have to have some cables which are put at the corners of the box girder for shear. This is the cross section which shows you that most of the cables are right at the top, in the top flange. This is the plan what you are seeing. Then finally the load test of the bridge was done, and the contractors chose Volvo trucks, which they had quite a few of them because they were transporting all their equipment across the bridge. So these Volvo trucks were filled with boulders, they were weighed, and then the IRC 2-lane loading of Class A was simulated. And of course, the big problem was in this 5.5 meter clear width, such a narrow bridge, how to put two lanes of these Volvo trucks. But I will just show you what they looked like in the actual situation. And the bridge load, of course, was found to be satisfactory because it had 95% of the rebound of the maximum deflection. Here you can see both the transverse section as well as the longitudinal section, how the two lanes of Class A were simulated. The actual photographs of these Volvo trucks, but of course in this picture you see only one side because the other is hidden behind the truck which is in the front. Here you can see there is hardly any space. So there were special drivers who were called, who knew how to maneuver the vehicles and who could, in this narrow space and this narrow gap between the two, still park the vehicles where they are required to be done in the during the load test. Here you can see another picture of the completed bridge. You can see the segments by these lines which are, these lines are all cast in situ segments and they are coming from both ends. I told you about how the deck had to be widened near the abutments, or rather beyond the abutments, because of this sharp turn at 90 degrees from all the vehicles which are coming and they want to go across to the other side of the bridge. So this was, I mean, these were some of the major challenges which had to be overcome. The materials, of course, the pre-stressed concrete superstructure, we could not make concrete more than M50 and that location. And the other concretes, of course, were well within the range of possibility. The pre-stressing cables all were 19K15 except a few which were 12K15. So it is a mix of 12K15 and 19K15 which were mixed, and you have a 2-cell modular strip seal catering to a movement of 150 millimeter because the central piers are monolithic with the deck. So you have got a integral deck with two plate piers, and the movement, all the movements are taking place only at the expansion joints which are at the end of the abutments. So there you require special strip seal joints and multi-cellular joints, and this 2-cell was found to be adequate for the movement which was anticipated to be 150 millimeter. Okay, thank you very much for your kind attention.
Thank you, Professor Tandon, for finishing exactly on time. And the next speaker is presentation of paper number 656, construction of four-laned cable-stayed road over bridge over Bardhaman Railway Yard, a case study by Shri Harsimran Singh. 15 minutes.
Mr. Harsimran Singh is officer of Indian Railway Service of Engineers, posted as DGM. He has experience of executing many railway-related infrastructure projects.
Respected dignitaries, my seniors and dear friends, good afternoon to all of you. I am Harsimran Singh, an officer of Indian Railway Service of Engineers, presently posted as Deputy General Manager at Kolkata Southeastern Railway Headquarters. I am thankful to IRC for giving me opportunity to present this paper on the four-lane cable-stayed road over bridge. I was associated with the project as project director on behalf of Rail Vikas Nigam Limited from inception until slightly before its completion. This is a brief overview. It was 227 crore project including approaches, but we will be talking about ROB proper, which had estimated cost of 122 crores. We had appointed detailed design consultant and project management consultant, and the tender was awarded in February 2012, and the ROB proper was completed in 2015. Approaches were taken up separately. It was to be done by PWD, and for that separate MOU was executed. The agencies involved in the ROB proper were Eastern Railway as the user, Rail Vikas Nigam Limited, RVNL as the implementing agency, Messrs. GPT Ranhill were the contractor, and Fresine were the specialized subcontractor for stay cable work. Messrs. Jacob CES were the DDC, and the PMC, IIT Roorkee was the proof consultant. CISIR was engaged for wind tunnel study. Messrs. Tu were the detailed design consultant on behalf of the contractor, and there was third party for inspection of the fabrication work, Mrs. QCC. The ROB proper was 188.429 meter span. There were constraints of 6500 mm clearance above the rail track, and the road surface could not be higher than 7500 millimeter. So entire superstructure had to be within a depth of 1000 millimeter below the road surface. And the entire main span was crossing the Group A Rajdhani route of Indian Railway. There were 9 railway tracks electrified and 7 platforms also. This is a view of the GAD. Initially, we had planned only 2 towers, which later on in detailed design became 3. The pylon was kept strategically outside the railway yard because it was nearly impossible to construct pylon inside the yard after crossing so many electrified tracks and platforms. And also in case of any yard accident, it would have been affected. Because of keeping the pylon outside, the bridge had become eccentric, as you can see here. The height of the pylon was dictated by the stability analysis as well as the economics. If we increase the height too much, then the stresses in the deck would decrease, but the cables requirement will increase, which are obviously very costly affair. And also there were pylon towers were sized adequately, 2.5 meter by 2 meters, so that easily stressing could be done inside the pylon towers. The height of the tower above the RCC deck was about 55 meters, and from ground surface it was about slightly short of Qutub Minar, so there were 3 Qutub Minars constructed. The deck is supported by 3 planes of cables. Each cable is anchored to the pylon and to the deck. On the main span side, we have cables connected to the longitudinal box girders, and on the back side, that is the minor span side, we have got very deep RCC beams which are cast monolithically with the 750 mm thick deep RCC deck. Parallel stand ST cables were used, which had 15.7 millimeter nominal dia strands. The strands had 7 numbers of ST wires, for corrosion resistance, the HD wires were having protective coating. They were then surrounded by wax, and in fact, the stand itself had a sheathing of HDP, and thereafter all the stands were covered with a deck. So there were about 3 to 4 barriers of corrosion. This is a three-dimensional view. We can see the the far end of the main span is simply supported over the pier, and the back span, which is the minor side, it is actually acting as an anchor for the main span. It is supporting the main span through cables and the pylon towers. The towers are connected at the top with tie beam. The bridge was obviously designed as per IRC codes, but since it was crossing railway tracks, IRS codes were also complied. The load combination